Our next speaker then is going to be Elitza Hristova from the Bulgarian Academy of Sciences, and she's going to talk to us about the GLN module structure of some relatively free algebras and applications to non-commutative invariant theory. Over to you.
Okay, thank you very much. I would like first to thank the organizers for the invitation to give a talk on this nice workshop. As the title suggests, I will talk about some classes of relatively free algebras, how to compute some information about their GLN module structure, and then how to use this in non-commutative invariant theory to compute some degree bounds of generators. So basically that's it. Let me start by fixing the notations. We'll work on a field of characteristic 0, and V will be a finite dimensional vector space over K with a fixed basis. And as usual, by K of Xn, we'll denote the free associative algebra generated by this set Xn. And this algebra is also isomorphic naturally to the tensor algebra of the vector space V. And as in the previous talk, we'll also consider T-ideals. And let me recall that a T-ideal is any ideal in K of Xn, which is closed under OK algebra endomorphisms. Or in other words, if we take any element from I, and if we replace the basis vectors x1 to xn by any elements from our free associative algebra, then we get again an element from the ideal I. And one example that will be very basic in our talk will be the example of the ideals IP for any integer p. This would be the two-sided associative ideal generated by all commutators of length p. And here I have also recall the notion of long commutator. So first we take the usual double commutator, and then we define commutators of length p using this iterative formula for any integer p. So if we take IP, it is not difficult to see that this ideal is an example of a T-ideal. Okay, and then the basic object in our talk will be the quotient algebra, K of Xn mod I, where I is a T-ideal. And this is a basic object in the theory of algebras with polynomial identities, and it is the relatively free algebra of rank n in the variety of unitary associative algebras that satisfy all polynomial identities from I. And a starting example is the symmetric algebra, which is obtained when we quotient our free associative algebra by the commutator, the usual commutator ideal. Okay, and now we introduce an action of the group of invertible n by n matrices with coefficients from K. When we have fixed our basis, we have a natural action of the group GLN on the vector space V, given by multiplication of matrix by a vector. And this action is extended to the diagonal action on the whole free associative algebra. And since any T-ideal is GLN invariant, we also get a natural action on the quotient. And there is one question that is very active in the theory of algebra with polynomial identities is that to describe the GLN module structure for the relatively free algebra for different classes of T-ideals I. And quite often, this question actually is formulated in another way in terms of actions of the symmetric group on certain modules. So, and in terms of co-character sequences, and many of the results that we will quote in the beginning will be done in this formulation. But in this talk, we'll only use the formulation as GLN modules and will translate all results in the language of GLN modules. Okay, and there will be two basic classes of T-ideals that we'll consider. That would be the ideal generated by commutators of length p plus 1, and also products of k such ideals for arbitrary k and arbitrary choices of these such integers. Okay, and let us first describe some known results. In order to describe them, we'll recall quickly how we describe polynomial GLN modules. So we recall that a partition with n parts is just a non-increasing sequence of non-negative integers. And we also recall that to any polynomial GLN, irreducible GLN module, we associate a partition lambda. And by V lambda, we will denote this irreducible polynomial GLN module, whose highest weight is this partition lambda. And also we recall that partitions we can describe in terms of Young diagrams, where these are diagrams of boxes, where the first row consists of lambda 1 boxes, the second row consists of lambda 2 boxes, and so on. So this is basically it. And now let me describe some of the known results. So if we consider a K of xn mod ideal generated by commutators, then this decomposition is known when P is equal to 1, 2, 3, and 4. So P equal to 1 is a classical case of the symmetric algebra. Its decomposition is quite well known. P equal to 2 is also a classical case. This is the relatively free algebra in the variety generated by the infinite dimensional Grassmann algebra. And it is also well known that the GLN decomposition in this case consists of such Young diagrams of a hook with this hook shape. And then the case of P equal to 3 is due to Vulichenko from 1978, and the case P equal to 4 is due to Stoyanova-Venkova from 1981. I have given here also the decomposition of K of xn mod I4, the case computed by Vulichenko, and the case computed by Stoyanova-Venkova is a bit complicated, so I have not given it here. And now when we consider products of such ideals, when our T ideal is a product of several, then there are also some known results. So when we have the usual commutator ideal times itself, this GLN module decomposition is computed by Mishchenko, Regev, and Zaitsev in 1999. And there are also two other known cases, which are given by Centrone in 2011. And Bumova and Drensky have given some explicit results for the kth power of the usual commutator ideal. Okay, this is what is known as explicit results for small values of P. And now there are some general theorems that give us bounds for the non-zero multiplicities for any T ideal. And the first one, let me recall it, is the theorem by Mitsur and Regev. It says that for any T ideal, there exist integers k and l, such that all non-zero multiplicities in the decomposition as a GLN module are supported in this hook diagram. Which means that from the k plus first entry of the partition lambda, all entries are bounded by the number L. And for the first k entries in the partition, we have no restrictions. So this is this theorem. And then Beryl improved it in 2005. By saying that, proving that for any T ideal I, there exist four integers omega 0, omega 1, s1, and s2, with omega 0 always greater or equal to omega 1, such that all non-zero multiplicities in the GLN module decomposition are supported in diagrams of this form, which means that the first omega 0 rows for the partition, they can grow arbitrarily large. And also the first columns can grow arbitrarily large too. n, and the rest is supported in this rectangle with height S1 and width S2. And this number is called the eventual arm length of the partition, and this is the eventual leg width, as arm width and leg width. Okay, and there are several cases in which Beryl computed omega 0 and omega 1. Let me give some of them which are relevant for our talk. So when we take the ideal generated by long commutators, at least of length 3, then W0, omega 0 and omega 1 are equal to 1. And if we take powers of such ideals, kth power, for example, for any k, then this leg width and arm width are equal both to k. And so this was for ideals that are generated by commutators of length at least 3. And when we take the usual double commutator, the statement is a bit different. So omega 0 is again equal to k when we consider the kth power. And for omega 1, we have a bit more complicated expression, again in terms of the number k. Okay, and our first goal, going back to this picture, will be, so we have some values for omega 0 and omega 1, and our first goal will be to give a value for S2 in the cases when our T ideal is generated by long commutators or is a product of such ideals. So let us move on to describing the method of finding this S2. So let us first introduce a bit more notation. So we'll call the commutators of this form pure, in which all the entries are basis vectors and nothing else. And Bn, this is a standard notation. Bn denotes the subalgebra generated by all pure commutators, and its elements are called usually proper polynomials. Bn is a GLN submodule of k of xn, and will denote by phi I the natural projection from k of xn to k of xn mod I. And the image of Bn will be phi I of Bn. So this will be the subalgebra of proper polynomials inside the relatively free algebra. And in the case when our ideal is IP plus 1 for some p, for shortness, we'll denote this projection not by phi I, but by phi of p, phi p. And there is one theorem of Drensky which will be very useful for us here. It says that as GLN modules, we have this isomorphism. So the relatively free algebra as a GLN module is isomorphic to the tensor product of the subalgebra of proper polynomials times the symmetric algebra of the vector space V with basis. So V was the vector space with basis xn. And this holds for any T ideal I. And why is it useful in our case? Because we can restrict the question of describing the GLN module structure to the subalgebra of proper polynomials. So we can first consider only this GLN module, and then use, once we find this GLN module, the structure as a GLN module, then we can use some branching rules for the composition of tensor products in order to find the GLN module structure of the tensor product. So our first result will be about the subalgebra of proper polynomials, and the result says that if we write down the decomposition as a GLN module, then a certain irreducible GLN module V lambda appears with non-zero multiplicity in this decomposition, if and only if lambda 1 is less or equal to p minus 1. So the non-zero multiplicities have this restriction for the partition. In particular, this means that our subalgebra of proper polynomials is finite dimensional, because there are only finitely many lambdas that satisfy this restriction, and that is usually not the case in general for other T ideals. The subalgebra of proper polynomials will not be finite dimensional. This is specific for the case when the T ideal is generated by long commutators. And I'm not going to talk about the proof. Let me just mention that one key ingredient in the proof is to use properties of products of commutators. And these are very classical theorems that when we take the product of two commutator ideals, we land in another commutator ideal. And this is the connection. If the two here m1 and m2, the two integers are arbitrary, then this is included in the T ideal generated by commutators of length m1 plus m2 minus 2. And if one of the integers is odd, then we have a better inclusion. So we are included in a smaller ideal, the ideal generated by commutators of length m1 plus m2 minus 1. But there is one additional property here that we add. And it is that we can still multiply two ideals of even length and land in the ideal m1 generated by commutators of length m1 plus m2 minus 1 if the last entry in the two ideals is the same. So these are basically three important properties that we use in order to show this restriction on the values of lambda. And once we have it, as we said, we use this decomposition given by Drensky, and we use branching rules in order to find the GLN module structure of the left side. And the general branching rule is the Littlewood-Richardson one, but in this case, we can use the special case of Pierry branching rule because one of the components is the symmetric algebra V, is not an arbitrary GLN module, but this one. And so using this standard branching rule, we obtain as an immediate corollary that if we write down the decomposition of the relatively free algebra K of xn mod IP plus 1 as a GLN module, then the values for the values of the partitions lambda, we have the following restriction that lambda 1 can grow arbitrarily large, but lambda 2 is bounded by the number p minus 1. And there is one important remark here is that this bound is exact, meaning that for any p, there is always irreducible GLN module V lambda, which appears with non-zero multiplicity in the decomposition, and for which the second value of lambda 2 is exactly equal to p minus 1. So this bound is exact for all p. And one example is given by the symmetric algebra. Here p is equal to 1. So p minus 1 will be 0. And this is exactly what happens. The first row of the Young diagram can grow. And from the second row on, we have zeros in the partition. And this also works for the other cases, not only for p equal to 1. And using similar methods, we can prove a similar result when we have a product of T ideals of this form. And this is the exact statement that if we write down the decomposition as a GLN module, then an irreducible GLN module will appear with non-zero multiplicity in this decomposition if and only if we have the following restrictions on the partition lambda. So the first k entries in the partition can grow arbitrarily large, but the k plus first entry in the partition is bounded by this number, the sum of the p1 to pk's minus 1. This is a generalization of the previous statement. Okay, and now we can move to the second part of my talk, which is about applications to non-commutative invariant theory. So let us first say what the topic of non-commutative invariant theory is. So in classical invariant theory, the idea of non-commutative invariant theory is to generalize somehow classical invariant theory, because the main object in classical invariant theory is the algebra, the symmetric algebra S of V, and then we consider the algebra of G invariants in S of V, where G is any subgroup of GLN. And classical invariant theory investigates the properties of this algebra. For example, when is it finitely generated? And we have here Hilbert's theorem that says that if the group G is a reductive subgroup of GLN, then this algebra of invariants is finitely generated. And one way to do non-commutative invariant theory is to replace S of V, the symmetric algebra, with the relatively free algebra, K of x n mod I, for arbitrary T ideals I, and then investigate the properties of this algebra of invariants, where again G is a subgroup of GON. And then Domokos and Drensky, they prove a non-commutative version of Hilbert's theorem, which says that the algebra of invariants of K of xn mod IP plus 1, so when the T ideal is generated by long commutators, so this algebra of invariants is finitely generated for any reductive subgroup G of GLN. And they also prove that it is finitely generated, as in the classical case, also for any maximal unipotent subgroup of a reductive subgroup of GON. So this theorem tells us that okay, so we are in this talk, we are going to take particular examples of reductive and maximal unipotent subgroups, and then try to find degree bounds, since we know that these algebras of invariants are finitely generated. We would like to find explicit bounds on the degrees of generators, homogeneous generators in a minimal generating set. And the explicit groups G that will appear will be these classical groups listed above. So the first 4 of them are reductive subgroups of GLN, and the last one, this is the subgroup of upper triangular matrices with ones on the diagonal. This is a maximal unipotent subgroup of GLN. And so by beta, we'll denote the maximal degree of a homogeneous generator in a minimal generating set. And since we're going to use Hilbert series, so our method for finding degree bounds will be by computing corresponding degree Hilbert series of algebras of invariance. Here I have also recalled the notion of Hilbert series for any finitely generated graded algebra. It is given by this formal power series here. Okay, and how are we going to compute Hilbert series? In the case when G is the group SON or UTN, we'll use a proposition by Benanti, Bumova, Drensky, Genov, and Koev, which says that if our A is a finitely generated graded algebra over the field K, such that each homogeneous component is a polynomial GLN module. And if we know the decomposition as a GLN module of A, then we can compute the Hilbert series of the algebra of G invariants using the following formula, where for the partition lambda, we have for this sum here over the partitions, we have some restrictions. When the group is SLN, this sum here is over all partitions with equal entries. And when the group is UTN, the sum is over all partitions. And one basic ingredient in the proof is the fact that if we take an irreducible polynomial GLN module, then it contains a one-dimensional invariant SLN subspace, or the whole module actually is a one-dimensional invariant SLN subspace if and only if the partition has equal entries. And for UTN, we have that every irreducible GLN, polynomial GLN module has a one-dimensional invariant UTN invariant subspace. This is the main ingredient in proving this result. And now we're going to use it and to compute the Hilbert series of the algebras of invariants, where the algebra A will be our relatively free algebra. Since we don't know the exact decomposition, we have given only some bounds, then this will mean that we'll obtain bounds on the Hilbert series. And first we consider the case of SLN. And the result is that actually in the case of SLN invariants, the Hilbert series is a polynomial, and we can compute, give a bound on the degree of this polynomial. In particular, this means that the algebra of SLN invariants is not only finitely generated, but also finite dimensional. And this bound here is not only a bound for the maximal degree of a homogeneous generator, but also for the maximal degree of any element in the algebra of SLN invariants. And here for SLN, we can actually give even a more general result for any t-ideal I. And so let us take I to be any t-ideal. And let us recall that we had in Barrow's theorem 4 integers, omega 0, omega 1. Omega 0 was the arm width, and omega 1 was the leg width, and this S1 and S2 were the dimensions of the square of the rectangle in the middle. So these integers, we take them from Barrow's theorem, and the statement is that if the dimension n is greater than omega 0, then the algebra of SLN invariants is finite dimensional. And in the Hilbert series is again a polynomial, and we can give a bound on the degree of this polynomial, and it is less or equal to n times S2, where S2 is this integer here. And furthermore, if n is even greater than S1, then we get even stronger bound on the degree of the Hilbert series, and it is that it is less or equal to n times omega 1. So this theorem tells us that not only omega 0 and omega 1 are important when computing degree bounds, but also S1 and S2 are, from Barrow's theorem, are important to be able to compute degree bounds on generators of algebras of invariants. Okay, so this was the case of SLN. Now we can move to the case of UTN. Here the Hilbert series is no longer a polynomial, it is a rational function, but with a simple form. And we can estimate the degree of the polynomial in the numerator. So this degree is less or equal to n times p minus 1. And as an immediate corollary, we obtain, so in this case, the algebra of invariants is not finite dimensional, only finitely generated. And as an immediate corollary, we get this estimate on the maximal degree of a homogeneous generator. It is n times p minus 1 if p is greater than 1, and it is 1 when p is 1. Okay, so these were the cases of SON and UTN. For the other three algebras, the orthogonal, special orthogonal, for the other three groups, sorry, the orthogonal group, the special orthogonal group, and the symplectic group, in a joint work with Drensky, we have given a similar theorem for computing the Hilbert series of the algebras of invariants. Only this time the theorem is over C. So from now on, we take our field K to be equal to the field of complex numbers. And the theorem has a similar, the proposition has a similar form as the previous one. We take A to be any finitely generated graded algebra over C, such that every homogeneous component is a polynomial GLN module. And if we know the decomposition of A as a GLN module, then we can write the Hilbert series of the respective algebra of invariants in this form, where the second sum has the following restrictions. When the group G is a symplectic group, the second sum runs over all partitions such that lambda 1 is equal to lambda 2, lambda 3 is equal to lambda 4, and so on. And when the group is ON, the orthogonal group, then the sum is over all even partitions lambda. And when the group is SON, the sum is over all even or odd partitions lambda. And again, here the main point is that if we take irreducible GLN module V lambda, then it has a one-dimensional invariant, for example, SP subspace, if this condition on lambda is satisfied. And it has a one-dimensional ON invariant subspace if this condition is satisfied, and so on. So basically, we follow the same ideas as in the proof of the proposition of Benanti, Bumova, Drensky, Genov, and Koev. And now we use this to give estimates for the Hilbert series of the algebra of invariants when we consider our relatively free algebras as A. And in the case of SP, we again obtain that the Hilbert series is a polynomial. So this algebra of invariants is again finite dimensional. And we have explicitly here given the maximal degree in the Hilbert series, and also then as an immediate corollary, the maximal degree of any homogeneous element in the algebra of invariants. How much time do I have? I'm almost done here, but okay, just I need 1 minute. Then for ON, SON, the respective algebra of invariants is not finite dimensional. So the Hilbert series is not a polynomial, is a rational function. But again, this rational function has a simple form. And we can estimate the degree of the polynomial in the numerator. In the case of ON, this is the estimate, and in the case of SON, this is an estimate for the degree of the polynomial. And as a direct corollary, we get that the maximal degree of a generator in the subalgebra of ON invariants is bounded by these numbers. And when we consider SON invariants, we get this bound on the maximal degree of a homogeneous generator. And one last remark here is to what extent are these bounds exact? These degree bounds on generators, to what extent are they exact? In the case when p is equal to 2, we can answer this question because in a previous joint work with Drensky, we have found explicit generating sets for this algebra of invariants. And comparing with these explicit generating sets, we see that the bounds are all exact, except in the case when G is the symplectic group. And now the question is what happens when P is greater than 2? And we don't know, but our expectations are that the bounds are not exact and they will be far from being exact because in our theorems, we use only restrictions on lambda 2 on the second entry in the partition. And we hope to get further more restrictions on other entries in the partitions in order to improve the bounds on these degrees. But still, we have some explicit bounds, and we're working on improving them. Yeah, okay, so this is the end of my talk. Thank you very much for your attention.
Thank you very much, Elitza. I think we've got time for one or two questions. So I have a quick, probably naive question. I'm not very familiar with noncommutative invariant theory. It's just something that occurred to me. So your T-ideals IP, the I1, quotienting by I1 gives you the symmetric algebra, right?
A quotient by I2 will give you the symmetric algebra.
So I would think of the quotienting by I3 as being some sort of generalization of that. So I wondered if you were to quotient by the right ideal to make the exterior algebra instead, so that would be quotienting by, I guess, products of squares, right? Squares in the so quotient by the ideal generated by squares, and you could generalize that to quotienting by ideals generated by cubes and fourth powers and so on.
Exterior, okay, okay.
So I guess some of your results would tell you something about that, but I also think probably there are stronger results out there if you're only dealing with not powers of commutators, but just powers of variables. I wondered if you could point me in the direction of any stronger results along those lines.
Will those be T-ideals? Could you say again what you're quotienting by again?
Oh, maybe this is the problem. Yes. Okay. So a quotient by x1 squared and x2 squared and x3 squared and so on. This should give you that should give you the exterior algebra.
Yeah, but that won't be a T-ideal. Some of the machinery of T-ideals will not work here.
Okay, I see. Thank you.
Yeah, sure. Maybe some similar results could be obtained, but using other methods.
Yes, probably. Okay. Alexander, you have a question?
Yeah. I have a question.
Okay.
Do you know the pi degree of these algebras?
No. What is a pi degree? Sorry, I don't know.
Oh. The pi degree is modulo the radical. It's a prime ideal, and the degree of essentially, what are these algebras modulo the radical?
Okay, I don't know, but I can think. I don't know. I haven't thought about that question.
Okay.
I think it's the symmetric algebra. The radical is just the commutator ideal.
Always for all these algebras?
Because all of them satisfy some non-matrix identity. Some identity which is not satisfied by 2x2 matrices.
Mm-hmm.
Can I ask a question? Oh, no.
Yes, go ahead.
Okay, so I have the following. If I'm not mistaken, there is such a theorem due Alexei Kanel-Belov. He is well known by his contribution to Specht problem. The theorem is as follows. If you have a relatively free algebra, the corresponding Hilbert series is the rational function. Is it true the same for invariant algebra? Is it always, I mean, it's Hilbert series is always rational function. Is it true?
Yes, this is again a theorem of Domokos and Drensky. The Hilbert series is a rational function for every reductive group.
I see. Okay. Thank you.
Okay, I think we should move on to the next speaker.
Okay.